I'd like to welcome everyone. I've got almost 60 people on the call so far, and I'm sure we'll have a few more joining. So welcome and thanks for joining the today's webinar. The Quantum Marketplace webinar series continues. QED-C is holding now roughly monthly webinars that spotlight a number of the QED-C members who are working in a particular area or segment of the quantum industry space. Today, we're going to be hearing from 3 companies that are working on quantum sensors, and I'm very much looking forward to these presentations. I'm Celia Merzbacher. I'm Executive Director of QED-C, and I'd like to welcome you. So just by way of sort of housekeeping, or I guess explanation, the quantum marketplace is really about connecting people, connecting potential customers with vendors, connecting our members with others in the community. And with that in mind, while QED-C certainly values your privacy and we generally don't share email lists with others, this is really a QED-C event here today. And so our plan is to make available to the presenters a list of the emails to the extent that we are able to capture them to the of the attendees. So if you're here, we'll make available your email address to the presenters. I think it's really important to helping those companies that are trying to grow their connections and networks to have that information. If you do not want us to share your email address, then send a chat to Mary Scott during today's presentation and we will make sure to remove it. But understand that it's just being sent within QED-C membership. So the format of these webinars is that each presenter will make a short 5-minute presentation, and that will be followed by a conversation, a moderated Q&A. Mark Wippich, who is leading that, is here to have the conversation, ask a few questions, and if you have questions you'd like him to ask, please enter them into the chat. So with that, I will turn it over to Mark. These are our presenters today from Sensorix, ColdQuanta, and AOSense. And so I will stop sharing and turn it over to Mark to introduce the first presenter.
Great, thank you, Celia. So Yuri, welcome, and we're looking forward to hearing what you have to say here.
Thank you, Mark. I'm going to share my screen just a second. Let me know if you can see it.
Great, everything looks good.
Great, yes. Thank you very much again. My name is Yuri Lebedev. I'm president of Sensorix LLC. I'm not a quantum scientist, but we do have Alexey Akimov, Professor Alexey Akimov, with us today. He's our lead scientist, and if you have any technical questions, don't hesitate to reach out to him. Our company is developing a quantum gyroscope, and with this slide, I just wanted to show you the current state of gyro technology. This chart is kind of a linear distribution of different technologies, and on the right side, you can see MEMS technology. That's a very low swap gyros, mass-produced, but they all have pretty low accuracy. And on another side, you have mechanical gyros that are still, to this day, it's an old technology, but to this day, it's hard to beat the accuracy, but it's very expensive and quite large in size. Mostly it's used for strategic and space application. What we're trying to do is kind of break that status quo and develop a quantum sensor that would be highly stable and sensitive, and would be priced reasonably, but at the same time have a very low swap as well. So our mission is to develop a microchip form factor quantum gyroscope using NV centers and diamond technology. This technology, besides rotation, can be used to measure electrical field, magnetic field, temperature, pressure, acceleration. And recently we discovered that team from MIT together with Air Force Research Lab and Army Research Lab are working on the atomic clock using NV centers in diamond technology with better than 10 to minus 13 frequency instability. So it's a pretty accurate clock, also using the same tech. In the center of the slide, you can see 5 microchip in a small box. This is actually the form factor of the gyroscope sensor element that we want to achieve. And the picture on the right, in fact, is the same chip, but under microscope. That chip was designed for magnetometry. It has microwave circuits, microwave antenna. It has a photodiode and optical filters. In order for us to adapt similar design for our purpose, we need to develop RF circuits, RF antenna. We'll have to find, and it's very important, find a chip scale light source, 520 nanometers wavelength and about 100 milliwatt power. And all of that we need to package with the chip controller, FPGA most likely, and put it in a small package, smaller than or close to MEMS gyros. So how the sensor works. As I mentioned, we're using negatively charged nitrogen vacuum system diamond as our sensing element. Yeah, you're probably aware that the nuclear has the mechanical spin, and we're in fact using this mechanical spin as a natural gyroscope. And so in order for us to use it within our sensor, just like any quantum sensor, we need to first prepare the quantum state of both electron and nuclear. And we're doing it using laser, microwave, and RF pulses. We prepared both electron and nitrogen nuclear state. Then we apply that state to the environment, which is rotation. And because of nuclear spin precession, the spin of the nitrogen nuclear changes slightly. And that change is then reported through electron fluorescence. And you can see on the right side of this slide, this is in fact the prototype gyro. And the red light is in fact fluorescence from the diamond chip. So our technology can be used pretty much in any industry, but we're really focused on the consumer electronics. Especially our focus would be great to get the smartphone applications. There are about 1.5 billion smartphones produced every year, and if we get 10% of that market with the gyro quantum chip, they could generate about $1 billion in sales. But we're not going to stop with the just a gyro, because the same technology can be applied to build the entire INS system on the chip. So it could be a next step. So now I'd like to open for questions, but we are interested to talk about funding opportunities, development partnership opportunities, and of course supply chain partnerships, because we do need to identify the light source that we need to make it a reality. Thank you.
Well, thank you, Yuri. Can you go back a few slides?
This one?
One more. One more.
One.
Yeah. So no, yeah, that slide right there. So, in talking with a lot of different companies doing quantum sensing, or companies that are looking to buy quantum sensors, there seems to be some misinformation out there about how, you're talking really chip scale solution here, so I think the audience would appreciate, how much is actually going to be on the chip, because this is a very small package.
And I think Alexei can answer, but we're looking at like a sandwich chip. So this one is the quantum control chip that controls or basically prepares the quantum state. It also the chip that contains the photodiode for readout purpose. Okay, so currently this chip again contains microwave circuit and microwave antenna, so we need to add RF circuits and RF antenna to it. Of course, we'll have to have a power control and FPGA control. So this is not, it will not be the same form factor as you see inside the box. It will be just a little larger, but it won't be, it will be very similar to MEMS device.
Wow.
Is entire assembly. Yeah.
Wow. Wow. Thank you for that. And so besides the, you know, the cell phone market, what other markets do you think that you could have once you have this solution available? What other markets do you think are the most promising?
Well, of course, the small UAV applications, our device, we don't intend to beat, let's say, if I go to this chart, we don't intend to beat mechanical gyros or, for example, laser gyros. And there are, of course, new quantum technology that are being developed, like cold atom gyros. There's NMR gyros. They also will be probably better than from stability and sensitivity than us, but would definitely be much better than MEMS sensors, and therefore they can be used on pretty much any industrial applications. It's again UAVs, car navigation systems, the agricultural navigation systems, of course for various small applications for the warfighter as well.
Yeah, yeah, thank you. And then there's we have time for one more question. You know, what is the from Scott Davis? Vescent. He's asking, you know, what is the line width frequency stability requirement for your light source?
That's Alexei's question.
So not really much. So central wavelength should be around somewhere 520 nanometers. Line width should, you know, like plus minus several nanometers is fine. Stability, intensity stability should be very good, because that's something we care about.
So what's the approximate line width that you need?
Oh, line width is some nanometers.
Okay, nanometers. Okay, nanometers.
Yeah,
I didn't know that. Thank you. Yeah, yeah. Okay. All right. So Celia, let's switch. If we have more time in the end, we can come back to some of these other questions. I think we should move on to Paul Lippman.
Okay, so I'll stop sharing. Thank you.
Yep. Thank you, Yuri.
Great. I'll go ahead and share my screen here. And then let me know when you are able to see the presentation.
Okay, see the presentation. We need it in presentation mode.
Yep, working on that right now. There we go. You seeing that okay?
Yep, excellent. Yep.
Great. Okay, well, thank you, and great to be here at my first QED-C presentation. I'm Paul Lippman, President of Quantum Computing at ColdQuanta. For those of you not familiar with the company, we've been in business for 15 years, headquartered in Boulder, Colorado. We're about 110 people right now, majority of those with PhDs in physics, engineering, deep IP portfolio, and we've raised over 70 million in capital. There are really three parts to our business: the quantum devices and machines, possibly where we're best known. We're one of the world leaders in developing small form factor, ruggedized, ultra high vacuum cells and the attendant physics packages. And these are products we use in our business, but also enable our customers and partners to develop quantum sensors and quantum prototypes. We have a research business that I'll talk about today, developing products in quantum positioning systems and in quantum RF. And then the quantum computing business, we are launching our first quantum computer later this year. That'll be a 100-qubit device available over the cloud. So as I mentioned, cold atoms are at the heart of everything we do, and depending upon the configuration of those atoms, it enables a variety of use cases. So in a 2D array, enables the quantum computer that I mentioned before. In a 3D lattice, we're developing ultra high precision atomic clocks, microwave clocks, and optical clocks. If we array the atoms in a linear form or in a ring, that is really the underpinnings of what we're doing in the precision navigation and timing arena that I'll talk about. And in more of a cloud configuration, we take advantage of the dipole nature of Ryberg atoms to develop ultra high sensitivity RF sensors, which I'll also talk about in a minute here. So moving to the GPS side, GPS, as we all know, underpins the world economy from a navigation and timing perspective, but it's a fragile system. It can be spoofed, it can be denied, and if you've ever driven in a busy city, you know you can drop GPS signal. So ColdQuanta is at the forefront of developing what we call quantum positioning systems, PNT systems. And a quantum positioning system is able to determine how fast it's traveled, for how long, and in what direction. So it only needs to know where it started to deliver extremely precise positioning without relying on external frames of reference. And one of the really, I think, exciting milestones for us in 2023, we'll be flying our first quantum gyroscope on a BAE test aeroplane in the UK in part of a government program that we're leading there, which is a milestone on the way to delivery of our full first field deployable quantum positioning system, which we'll have ready later in 2025, early 2026. Turning now to quantum RF, ColdQuanta is pursuing two RF research programs, both focused on ultra miniature sensor heads. And you can see kind of illustrations here on the left. They're both kind of roughly the size of kind of an inch on the side, size of a quarter. The first program incorporates a small atom vapor cell with a resonant RF cavity, and this is for sensitive detection of very narrow frequencies, for example, in stealth communication, advanced radar applications. And the second focuses on detection across a broad array of frequencies from sub-gigahertz through terahertz, with applications to broad spectrum communication, signal detection finding, and terahertz imaging. So if you think about then the application to industries, this really cuts across a broad swath of industries, really driven by substantially reduced antenna footprint. So if you think about in telecoms, where you have telecom towers with these multiple antennas of different sizes and configurations, that can all be replaced by extremely small, extremely lightweight, extremely rugged quantum sensors, enables increased spectrum utility and efficiency, and actually a broader array of spectrum that can be utilized, reduction in transmitter power requirements as a function of increased sensitivity of the antenna, more effective in building communication, and ultimately supports the development of quantum communications and the future of quantum networks. So in terms of how we're looking to engage within the QED-C, we're looking to partner in the development and commercialization of the full end-to-end systems and on go-to-market, and of course, always interested in potential customers for our quantum products and devices, as I said before, in supporting our partners in the development of their quantum sensors, and certainly always interested in potential additional investment. So thank you very much, and I'm happy to take any questions.
Great, thank you, Paul. So the first question, can you go back to your quantum positioning system? Or in the this one or the end markets, but let's leave this one for now. You know, so ColdQuanta is very bullish, it seems, on the future of finally getting quantum positioning systems deployed. You know, in terms of the market, where does ColdQuanta see, you know, the most interesting potential for commercialization?
Yeah, great question. I think there's a question of near-term market and kind of mid to longer term market. So I think in the near term, obviously there's a variety of applications in the defense arena across kind of the totality of potential platforms, whether that's airborne, landborne, undersea, certainly a lot of interest in space navigation. Longer term, we believe that a significant opportunity for commercialization exists around autonomous vehicles. So if you think about the precision, stability, and time-based requirements for a truly autonomous vehicle, I'm not talking here about kind of today's level 2, but really kind of getting more to the level 4, level 5, that requires a level of precision and a level of kind of over time capabilities that simply are not possible with GPS systems. And so we see significant opportunity there as the SWaP gets reduced to provide that critical component of the delivery system.
Great, great. Thank you for that. And I know this is a quantum sensing webinar, but can you go to your quantum computing slide where you mentioned you're going to have a quantum computer later this year?
That's right.
I think it's, yeah, 100 qubit. That's pretty phenomenal. You know, what, you know, and this is sort of a different style of question, but you know, cold superconducting quantum computing and even some of the ion quantum computing has really garnered a tremendous amount of press, right? And you know, how do you see sort of getting in more of the limelight or, you know, advantages that the neutral atom approach has that ColdQuanta is working on?
Yeah, so look, I mean, I think it's still really early days in quantum computing, right? And cold atoms, the new kid on the block, from I think you know, as you rightly said, superconducting, a lot of press. Cold trapped ion obviously has been really on the forefront recently. But if you think about the intrinsic challenges in quantum computing, both in terms of qubit count and connectivity, we believe, and certainly our kind of fellow cold atom quantum computing companies believe, that cold atom has the most promise in terms of the long-term roadmap, both in terms of scaling qubit count, but also in terms of scaling connectivity, right? We can ultimately get to connectivities that are an order of magnitude greater than are possible in the superconducting arena. And what's kind of interesting, if you think about cold atom, we're cooling atoms down with lasers, and we're cooling them down 3 orders of magnitude colder than's possible with superconducting, and we're doing that with devices that are operating at room temperature. So if you think about what it will take to get to 1,000 qubits, much less 1,000,000 qubits, to do that with superconducting requires really kind of science discoveries along the way, and certainly with photonic quantum computing probably requires several Nobel Prizes to be won to kind of get to that end state. Whereas with cold atom, we have clear line of sight to what it would take to get from 100 qubits to 1,000 qubits and beyond, and doing that while decreasing the form factor over time. I mean, ultimately, these things will become rack mountable. So, you know, and our belief is, A, it's early day, B, cold atom has a lot of promise, and C, you'll see us start to talk very publicly about some of these technologies in the coming months. Great,
great, thank you for that. One last question, and then we'll move on, and then come back for more questions in the end. Can you go to your quantum field sensor slide? Yeah, so one of the themes that's coming up, it's not necessarily a bad theme, but many are saying that you know, quantum RF sensing is mainly about receiving signals and not being able to transmit signals. How do you look at that? So
absolutely correct. At least the programs we're focused on today are about receiving signals for a variety of reasons. If Dana's here on the call, he may well have joined. He could certainly talk about, you know, how we might approach transmitters as well. But one of the things to take into account, if you have a receiver that's dramatically more sensitive than current conventional receivers, that then reduces the power requirements commensurately for the transmitter. So you get that benefit of inherently more sensitive receivers mean that the transmitters themselves have to be less powerful. So if you think about
oh yeah, that's a good insight. Thank you. Yeah. Okay, thank you, Paul. Celia, I think we should move on to Brent from AOSense.
Go ahead and share the screen here.
You're on mute, Brent.
Okay, let me know if the screen comes up.
It's up.
Okay, great. And so I'll go ahead here. Okay, and we really appreciate my name is Brent Young. I'm president of AOSense. Really appreciate the opportunity here to describe what we're doing here at AOSense on quantum sensing. And let's see. And although the quantum sensors have an exciting potential for enhancing capabilities in defense, national security, and commercial applications, although AOSense has participated in projects addressing a broad range of these applications, our primary mission has been to transition quantum atomic sensors and advanced atomic clocks from physics laboratories to fielded systems that will improve navigation and timekeeping in GPS-denied environments. Atoms have the capability to ultimately support navigation with inaccuracies less than about 5 meters after 24-hour navigation time. This represents a 200-fold error reduction relative to the typical half nautical mile per hour navigation errors of conventional aircraft navigators today in the absence of GPS. The world's best atomic clocks, of course, have achieved much lower errors than we target here. However, those are laboratory clocks that are unsuitable for field applications. Our objective is to enable operation on moving platforms while maintaining performance exceeding that currently available with existing mobile atomic clocks. One of the appealing aspects of quantum atomic technologies is the broad range of modalities in which they can operate. For conventional sensors, high performance gyroscopes and accelerometers employ very different technologies. However, the commonality of atomic devices has enabled AOSense's modest 30-person staff to contribute significantly to the broad range of quantum devices indicated here. A green check indicates AOSense's development of a laboratory prototype. We give ourselves a gold star whenever an independent external laboratory validates our sensors. When AOSense first started developing quantum atomic technologies in 2004, component technologies suitable for fielded systems in dynamic environments were severely lacking. Over the past 17 years, AOSense has developed a variety of enabling technologies, which we now sell commercially. So this next slide shows a variety of AOSense's photonic, electronic, and vacuum products that enable robust, low-swap quantum technologies. For example, our lasers and laser drive electronics provide high performance in low-swap packaging. The unique feature of our optical isolators is that they provide much higher transmission at 780 nanometers and 850 nanometers than competing miniature isolators. We sell our high-flux cold atom beam system to premier research groups around the world. They enable these groups to focus on physics research rather than engineering an atom source. Within the next few years, quantum atomic gyroscopes will revolutionize high accuracy GPS-denied navigation. In 2021, just a couple months ago, DARPA approved for public release AOSense's 2009 gyroscope results from our precision inertial navigation systems effort. So those results are shown here. On a modest budget, the gyroscope achieved truly exceptional angle random walk and bias stability. Imagine that you take a circle and divide it into 360 degrees, then divide a degree segment into 1 million parts to get 1 microdegree angular subdivisions. You would need to wait 1 hour to observe a 1 microdegree drift of the pin's gyroscope. This graph compares the performance that quantum atomic gyroscopes in general, that's what this bubble is right here, can achieve relative to a variety of other conventional technologies, which have benefited from over $1 billion funding over about 50 years. So it's really rapid progress we're seeing here. Subsequent And the red line here indicates the bias instability of the AOSense gyro. Subsequent AOSense research has focused on reducing swap and enabling robust operation under high dynamics. The next step is combining multiple quantum atomic inertial sensors into an atomic IMU, or inertial measurement unit. Many consider quantum atomic inertial sensors to be relatively immature technologies that are years away from practical applications. However, AOSense first completed and shipped a portable single-axis quantum atomic gravimeter over a decade ago. Although this low-budget portable system traded off performance relative to previous larger systems, the strength of the atomic reference is evident in the observation shown in the plot on the right of the lunar solar variations due to the relative motion of the sun, earth, and moon. After demonstrating portable sensors, our next step was to initiate the development of mobile sensors, which can actually operate while on a moving platform. An AOSense IRAD project developed the quantum atomic gravimeter on the lower left, which can function in any orientation. A van transported this sensor starting in the AOSense loading dock, heading up to Skyline Boulevard to the west, returning to AOSense, continue to Mount Hamilton to the east, and then returning to AOSense loading dock. The gravity measurements, which we collected in a stop and go mode, exhibited good retrace for measurements of local gravity at various altitudes. Further development should support mobile gravity data collection. Finally, we are excited about the prospects of quantum atomic absolute gravimeters for geophysical exploration and national security applications. This table compares the target performance for AOSense absolute gravimeter under development with the performance of competing technologies. The boxes below highlight the significant volume reduction that we anticipate. We would encourage you to contact us with any questions you have about either our R&D services or products. Thanks for your attention.
Thank you, Brent. Thank you. So can you go back to, I think it's, I sort of want to do this backwards, but go back to 6.
Okay, let's see. So I'm just looking for the slide numbers here. Okay,
Yeah,
that's 7.
That's
okay,
7, one more. Yeah, so,
Okay.
so you actually, so this is a real working unit that you put in a van.
Yep.
And you drove it around and you made measurements and you measured the difference in mellogals on repeated runs of driving it around to show that it works.
Yeah, that's right. So in the plot you see is kind of a time sequence on the horizontal axis. It indicates the run number of different measurements we make. And then the vertical axis indicates the gravity measurement, where it's relative to the measured value in the AOSense laboratory. And the US NGA had made a measurement of what the gravity was in the AOSense laboratory. And so we had a good measurement for that. And the USGS had measurements for these other locations, particularly for Mount Hamilton. So that's why we do a comparison there between the 277 plus minus 3 milligal that we measured versus the 268 from USGS reports.
Yeah, it's really fantastic. I've never seen anything like this publicly. Well, I guess this is QED-C membership right now, but I haven't seen data like this before. Can you go back to, I want you to go back to your pin slide.
Okay.
Well, I already had a question prepared here, but John Kitching actually is asking one of my questions as well. He's saying spectacular results on pins. Brent, are those performance specs publicly documented? And you and I talked about this a bit, Brent, before. You have only been allowed, as of 2021, that you have in your slide here, you know, that we asked you to put there, because you have these results as of 2009, but because of various restrictions of US DoD, you were not allowed to release this data until now. Is that correct?
Yeah, that's right. This is the first time I was actually able to publicly present it in a non-restricted audience. So, but and to answer John's question, yes, there's a review article on quantum sensing that's out for publication. It's not been published yet. Once it is published, then I can provide a reference for it. AOSense is not one of the co-authors on it, but it included our results.
Yeah, that's fantastic. So So is it safe to say that you have continued to work on your gyro and it's better than what you're showing here?
Yeah, if you search for you know, kind of DARPA press releases, they'll talk a little bit about in this time frame after 2009 of, you know, various program managers will talk, you know, will talk in trade journals about the types of things they were working on, which is basically trying to take performance that were demonstrated under static conditions and try to transition them to dynamic conditions. And so, you know, AOSense is certainly engaged in various projects to advance the state of the art beyond what was achieved in 2009.
Great, great. Wow. You know, one other question. So what do you see now for AOSense and the market in general? You know, gyro, quantum gyros, you know, research has been going on, what, really since about 2004 or 5, correct me if I'm wrong, where the funding really started to accelerate. Where do you think it goes from here now? You know, like in terms of, you know, and what is the next, how it better said is, what is the next steps for AOSense in terms of, you know, commercializing this technology? What are you focused on?
Well, you know, we are interested in supplying sensors. So, and we're happy to either provide them as single axis, you know, gyroscope accelerometers, or we're happy to integrate them together into an IMU, similar to previous speakers. And, you know, and also, you know, kind of have the similar vision to Paul and others, that you start kind of with some of the military applications that are most demanding and have the strongest need to operate in a GPS denied environment. But then over time, as you know, we develop you know, ASICs and integrated photonics for really reducing the swap of these devices as well as the cost. Then yeah, we're also excited about meeting the needs of various commercial applications. You know, certainly there are those applications out there right now, commercial navigation that needs to be done underwater and they can't use GPS signals. So they're out there, but the thing is that they're more cost sensitive than you know, certain DoD applications. So we need to really do some significant engineering to really bring down the cost. But you know, the systems, you know, once we really refine them and perfect them for the DoD applications, I really see no reason why we can't, if we find the right sources of funding for doing the development, see no reason why they can't really be benefiting commercial applications as well.
Great, thank you so much. And I want to, the next question I want to ask you, and then I also want to ask Paul and Yuri as well, because, you know, all three of you are talking in a similar fashion around, you know, accelerometers. I know Yuri is going for really, really small, you know, but you know, but you know, and you and Paul are talking more about addressing various aspects, including super accurate systems. So the first question I want to ask, you know, is what do you see as, in terms of the technology today, what are some of your most challenging TRL situations?
Well, the common one that always comes up are the lasers. You know, if you know, our laser demands are a lot more aggressive than what Yuri requires for the NV diamond systems. So we do need to have, you know, say less than 100 kilohertz line, you know, on the neighborhood of 100 kilohertz line with or below for optimal performance with the cold, you know, either cold atom or thermal beam systems. So that's, and then you have to have mode hop free operation for long periods of time. And you know, and fairly long lifetime. So that certainly that is, the lasers is one of the key concerns. So we have to make certain that there enough funding is going in that direction to support the high reliability, high performance devices that we want.
Yeah, I second that. And for us, of course, it seems like laser community in the whole have almost no 215 nanometer laser capabilities. So it's a green light, and green light in a microchip form factor is hard to come by.
Yeah, I'll second that as well. I mean, lasers certainly, both in terms of lifetime, but also in terms of kind of looking further out in terms of form factor reduction, PICS integration becomes increasingly important.
Great, and thanks, Paul. Thanks, you mean 520 nanometers, right?
Yeah, 520. Did I say something different?
I think you said 250 nanometers,
No, no,
but that's okay.
520.
20,
Yes.
yeah, right, okay. So now here's another question that you know, I'm certainly of the belief, and I think others are, that they're one way to help, I think, the QED-C community from an economic standpoint and getting to commercialization faster is enabling some more partnering between maybe some of the larger companies and smaller companies, and not just getting funding from, say, DoD, or getting funding from outside professional investors, et cetera. But, you know, how do you, so let's start with Brent. How do you see, what are you looking for along those lines? Are you looking to partner with larger companies to bring this to market faster, or other companies?
Yes, absolutely. I think it'd be bad news if we were just kind of flying around blind, not knowing exactly what this large system integrators wanted. So we are very interested in teaming up with large aerospace companies that currently are building and selling to the government various platforms. And we want to try to work with those organizations to figure out what are the requirements of their platforms and design the next generation of sensors to be compatible with those platforms. So yeah, it's very important.
Great.
Yeah, we're similarly, I mean, we're talking to certainly on the quantum RF side, the large both mobile carriers, telecommunications company, telecommunication equipment companies are all looking at and trying to determine how does quantum enable, support, and extend their roadmaps. There's a lot of interest around quantum internet communications, and so similarly, we're engaging in strategic conversations with a number of the major players in those industries.
So, Paul, have you also looked at doing that with your quantum navigation?
Yes, also with quantum navigation, but in a different part of the kind of partnering space, and similar to the comments just made with the large aerospace and defense players.
Great. And Yuri, you have any comments on that?
Not really, but again, we're really focused on low swap. That's our key priority, to hit the low swap, and applications, of course, mostly commercial applications. I've seen some questions here about ITAR, and that's one of the issues why we kind of try to focus on more of a commercial area with precision that would not require any type of expert control. But of course, at the same time, would be much better than current technology available today in the market.
Yeah, actually, I'm glad Celia brought that up. I had that on my list. Brent and Paul, to the best of your knowledge, how much is export control hurting your ability to go faster?
Well, it really limits our ability to communicate with various organizations. And, I'd say, up to maybe a couple of years ago, I didn't feel like it was limiting us very much at all, because I felt like, there's really sufficient funding, but the funding has been a little bit slower the last few years. And so then it would have been a little bit nicer to be able to communicate information more effectively, to go out and be able to raise funds more quickly.
Yeah. Paul, you want to make a comment?
Yeah, I mean, similar. Obviously, ITAR certainly in a number of the programs, especially on the RF side, is a consideration. Interestingly, less so on the quantum computing side, and actually we're standing up that capability in our UK office, and similarly with the positioning systems as well. But it is a consideration. I wouldn't say that it's slowed down our development, to your question, Mark, but as we think about the addressable markets and scope and scale for expanding, especially in Europe, that is definitely a consideration.
Okay. Into a little bit more detailed technical questions. There's a question from Michael Larson. How in terms of the quantum navigation, have you overcome the loss of contrast under rotation, or do you still need gimbals? Anybody want to answer that?
That's not really detail I can go into here.
Yeah.
Okay.
Sorry.
Okay. All right. And then let's see. I think you guys answered this, but just to make sure it's crystal clear, Scott Davis asked any thoughts on, further thoughts on commercial applications for gravimeters. Brent, do you want to take that one?
For gravimeters, I mean, the main things I'm aware of are, geophysical exploration. I mean, again, there are two different types. There's the mobile gravimeters that can actually make measurements when you're in motion. There's a portable gravimeter that is, it has to be operating statically, but it's something that's lightweight, easy to carry around. They have kind of different application base. The mobile is more for, gravity-aided navigation enhancement. Whereas the geophysical static gravimeters are more for geophysical exploration. It could be looking for a wide variety of different natural resources. It could be for real-time management of resources, things like monitoring an oil wells over time to determine how you're pumping out the oil while you're replacing it with water. It could be, I've applications in volcano monitoring that, again, that would be more the geophysical devices. And then finally, if you're looking for underground structures or tunnels, that's another application for the high performance ones, or a mobile gravity gradiometer. Those are some of the applications I know. There are certainly a lot of them out there. Those are some of the keys.
But I guess which one out of all those you just mentioned, which one do you think has the most customer pull?
I'd say in the end, the biggest one will be the geophysical exploration, but the customers there, it sounds like, don't like to put a lot of money into R&D, so that's probably not who's going to pay for it.
They don't. They absolutely don't. What is it that oil industry puts in less than 1% into R&D or something of their budget, right?
Yeah.
That's a big budget, but
yeah,
crazy. Let's see. So,
by the way, maybe if I could have a second, just coming back to Mike Larson's question, I think he can look up papers, say, by our AOSense's chief scientist, Mark Kasovich, for his work at Stanford, where he talks about, how to deal with, in an academic setting, how he's dealt with mitigation of the effects of rotation. There are some ideas you can glean from that's kind of in the open literature, and it is definitely an important question, an important problem that everybody has to deal with if they're trying to do these types of devices on moving platforms.
but you could, if you could have a conversation that was protected under secrecy or ITAR, right?
Yes, we have to kind of distinguish things that are restricted by the government versus proprietary. But yes, there certainly are things that.
Okay, so he should reach out to you, and he should reach out to you, though, right?
Yeah, if he's interested, we certainly would be happy to talk with him.
Okay. And then the other thing is, I think a little bit back, Paul. I don't know if you want to answer this, but Santanu from Corning is asking, what's the advantage of neutral atom over ion trap quantum computing? I think you sort of answered that, but if you want to add some color, I'll give you that opportunity.
Yeah, I'll answer it very, very quickly. I mean, look, at the end of the day, I think the reality is there'll be multiple modalities that will prevail in quantum computing, and it may well be different modalities for different use cases. I think fundamentally, when you compare trapped ion with cold atom, one of the advantages with cold atom obviously is the atom's neutral. We can pack them very close together. We could have 1,000 qubit array kind of in the width of a human hair, but obviously with trapped ion you have the Coulomb repulsion, so scaling becomes more challenging. And in terms of implementing gates, it's clear how we scale that with cold atoms. It's far from clear how that scales with trapped ions, and thus the point that, with cold atom, we believe it's an engineering pathway to scale, whereas with trapped ion, there are some scientific discoveries that have to happen along the way. But I will caveat by saying, obviously, it's early days overall for the industry, But again, we do believe that neutron atoms is inherently a more scalable approach.
Great, thank you, Paul. Another question from a bit back, Michael Radunsky asked, what is the application in the bottom left of the slide? Could we see Yuri's presentation really quick?
Yeah.
Maybe Brent, stop sharing.
Okay, sure. Yep. There we go.
Just a second. All right, let me share the screen.
I think it's slide 5, right?
Slide 5.
Yeah, so you got two brains melding together there.
Oh yeah, this one. Yeah, because in fact, I think you all know and probably seen some literature about NV-Sanderson diamond magnetic and electrical field sensitivity. It's very, very high, and so there is an application for basically reading your thoughts with the quantum chip. So. But I mean, that is true. That's going to come in the next about 10 years where you'll put a little hat on your head and pretty much can communicate with each other, over distance.
So through magnetic field sensing.
Exactly, yeah. Both electrical, because, your neurons firing, so you get the electrical field and, you can map the entire brain. And because, again, that's the beauty of NV-Sanderson diamond and colors in diamond is that you can make the sensors very, very small. So it's like a grain of salt, kind of small.
Thank you for that. And then and I guess Brian Miles asked, how can quantum RF be used to improve efficient use of existing RF spectrum? Paul or Yuri, you want to take that?
It's maybe Paul's question, probably. Alexei might answer that question as well.
Yeah, this is more to do with, and again, I'd ask if any of our technical experts from ColdQuanta are on the line to feel free to jump in, but this is really to do with the sensitivity to very narrow line width. So it's a combination of being able to utilize much narrower bandwidth and at the same time utilize much more sensitive receivers. So rather than if you think about multiple antennas for multiple frequencies, to have a single antenna that can span from kind of 100 megahertz all the way up to terahertz gives you the capability to kind of do away with those complex antenna towers from a mobile perspective, and at the same time where frequencies becoming increasingly expensive when you look at the amounts being paid at auction, to be able to make more efficient use has kind of tremendous benefits from an economic standpoint.
Great, thanks, Paul. Well, I think with that, is there any more questions? I think some of the questions that are left have already been answered.
I had one question, and then I'll put up a slide with the schedule of our next upcoming events. But I'm always sort of sensitive, and you see examples in current technology of cybersecurity issues with hardware, and I'm just curious if that's something as you're developing your products, whether that's sort of considered upfront or whether it's something that is maybe dealt with later. And how important is that to your customers?
I'll jump in on that. I came out of the cybersecurity. I came into quantum out of almost 2 decades in the cyber security industry. I would say I think kind of from 2 perspectives, both in terms of how we treat cybersecurity. Kind of internally, that is becoming certainly for ColdQuanta an increasingly important area of focus, both from the standpoint of compliance, but also in terms of the recognition of the need for really significant cybersecurity controls to protect IP and to protect the sensitivity of some of the programs and topics that we work on. In terms of customer kind of questions and customer demands around cybersecurity, we really see our role as providing the fundamental kind of physics and physics packages, but ultimately looking to partner with those who can provide the full end-to-end integration and systems. And so in that discussion and in those considerations, absolutely cybersecurity is something that we are looking to build into the design from day one, rather than as an afterthought. And that's absolutely just kind of a best practice from a cyber perspective, because if you're not designing from day one for cyber, but rather seeking to do that as an aftermarket, you're going to leave a lot of vulnerabilities wide open to potential compromise.
Thanks. That's good to hear, encouraging. So I will share my screen and
Awesome.
just leave everyone with a reminder for the schedule of events. We've had a couple of outstanding quantum marketplace webinars. Information is, we're editing these and posting them both on the member site and ultimately on the public site. We didn't sort of do all the development work to be able to do that on a turnkey basis. So we're kind of working that out with the first couple, and hopefully it'll go smoothly moving forward. So we'll put out information when that goes live. Meanwhile, we're scheduling the next event in July on the 27th. That one's going to focus on cryogenic technologies and companies in the membership. And we're thinking the one in August will be about quantum entanglement sources. If you have suggestions for future webinars, please feel free to reach out to any of the QED-C staff and let us know. If you have feedback on how we can improve this program, we'd love to hear from you as well. So with that, I'd like to thank all of the speakers for their presentations. Thanks, Mark, for your outstanding job as moderator. And we look forward to seeing everyone on July 27th. Thanks.